Hello, my friend, and welcome to Orbital Dreams. Tonight we're going to explore one of the strangest ideas in science. What if the universe is not quite what it seems? The space around you feels real. The stars feel far away. The world feels deep, solid, and endless. But some clues in modern physics suggest something much stranger. That all this depth may come from hidden information beneath reality itself. Black holes seem to hold part of the secret. Light gives us another clue. And the deeper scientists look, the more it seems possible that space itself may not be the beginning of the story. So get comfortable, let the day fade away, and let's slowly follow one quiet question into the dark. What if the universe is a hologram? Chapter 1. The strange idea that reality may not be what it seems. Few ideas in modern physics are as fundamental and quietly exciting as the possibility that the space around us, the depth of the cosmos, and even the feeling of living inside a vast three-dimensional world may arise from something deeper. At first, the idea sounds almost too strange to take seriously. The universe feels solid enough. A table feels like a table. A wall resists your hand. The floor holds you up. Stars look distant. Galaxies appear to float across enormous stretches of space. Everything about daily life tells us that we live inside a world with height, width, and depth. A world where objects occupy places, where distances separate one thing from another, and where reality seems to unfold in a continuous stage around us. But science has often shown that the world of ordinary experience is not the deepest layer of reality. The sunrise feels as if the sun is moving around Earth, but Earth is turning. Solid matter feels full and continuous, but atoms are mostly empty space, held together by forces and quantum rules. Time feels the same for everyone, but relativity teaches that motion and gravity can change the rate at which time passes. Again and again, the universe has gently corrected our instincts. It has not made reality less real, it has made reality more surprising. The holographic idea belongs to this same tradition. It does not simply say that the universe is a trick, or that life is an illusion, or that the world is somehow fake. That would be too shallow, and it would miss what physicists actually mean. The deeper idea is more careful. It asks whether the information needed to describe everything inside a region of space might be stored in a way that is not spread through the entire volume, but encoded on a boundary surrounding it. In other words, what we experience as a spacious interior might be describable from a surface. That sentence may feel abstract, so let us slow it down. Imagine a room. You can walk through it, touch the furniture, notice the distance from one wall to another, and feel that the room has an inside. Our intuition says that all the information about the room belongs throughout that interior space. The air is inside. The objects are inside. The light is inside. The positions and motions of everything seem to require the whole volume of the room. But the holographic principle suggests that, in certain deep theories of gravity, the full description of a region may be related to information on its outer boundary. The inside may not be independent in the way it seems. This does not mean that the room disappears. It does not mean that your experience is meaningless. It means that nature may have a more economical way of keeping track of reality than our senses suggest. Depth may be something that emerges from a more basic pattern, much as temperature emerges from the motion of many particles. Temperature feels like a simple property. A cup of tea is warm. A winter window is cold. But underneath that simple feeling lies the motion energy and arrangement of countless molecules. The warmth is real, yet it is not fundamental in the same way the microscopic motion is. It is an emergent feature, a higher-level description. Space itself might be similar. It may feel like the most obvious thing in existence, the silent container in which everything happens. But in modern physics, space is no longer treated as an empty stage. In relativity, space and time are woven together into spacetime, and spacetime can curve in the presence of energy and matter. Gravity is not just a force pulling objects through space. It is connected to the shape of spacetime itself. This was already a profound shift. It told us that space is not passive. It can bend, stretch, ripple, and guide motion. Quantum physics made the picture even stranger. At very small scales, nature does not behave like a collection of tiny clockwork objects with exact paths and perfectly defined properties. Instead, quantum systems are described by possibilities, probabilities, and relationships. Particles can behave like waves. Objects that have interacted can remain linked in ways that do not fit ordinary intuition about separation. Measurement is not just passive observation in the everyday sense. It is part of how definite outcomes appear from quantum possibilities. The great challenge is that relativity and quantum physics each work extraordinarily well in their own domains, but they do not fit together easily when gravity becomes both very strong and very small. Black holes are where this tension becomes impossible to ignore. A black hole is not simply a cosmic drain. It is a region where gravity is so intense that beyond a boundary called the event horizon, light itself cannot escape. That boundary is not a physical wall you could touch. It is a point of no return in spacetime. When physicists studied black holes carefully, they found something astonishing. Black holes appear to have entropy, a measure connected to hidden information and the number of possible microscopic arrangements that could produce the same large-scale appearance. But the entropy of a black hole does not behave the way ordinary volume-based intuition would suggest. It is connected to the area of the horizon, not the volume hidden inside. This was one of the clues that led toward holographic thinking. Somehow, the boundary seemed to matter more deeply than expected. This is where the word hologram becomes useful, though it must be used with care. A familiar hologram can make a flat surface appear to contain a three-dimensional image. The image has depth, but the information that creates that appearance is encoded on a lower dimensional surface. The universe, if holographic in the scientific sense, would not be a simple picture floating on a wall. It would be far more subtle. The comparison is not meant to say that reality is made of light on glass. It is meant to suggest that depth and volume might be encoded in a way that resembles how a hologram stores more dimensional information on a lower dimensional structure. So when we ask, what if the universe is a hologram, we are really asking a deeper question. What if space is not the starting point? What if distance, depth, and geometry emerge from information? What if the universe is not built first from empty space that then gets filled with matter, but from relationships that give rise to space itself? These questions do not have final answers yet. They belong to the frontier of theoretical physics, where scientists search for a theory that can unite gravity, quantum mechanics, and information into one coherent picture. It is important to be honest about the uncertainty. The holographic principle is not the same as saying we have proven that our entire universe is literally projected from a cosmic screen. Some versions of holography are mathematically powerful in special kinds of universes used as models. Our actual universe is more complicated. It expands, contains dark energy, forms galaxies, and does not perfectly match the simplest settings where holographic ideas are best understood. Still, the principle has become one of the most important clues in the search for quantum gravity, because it connects black holes, entropy, information, and space-time in a way that feels too deep to ignore. This is one reason the topic is so powerful for the imagination. It changes the question from what is the universe made of to how is the universe described. That shift is enormous. For centuries, physics often searched for smaller and smaller ingredients: molecules, atoms, nuclei, protons, neutrons, quarks, fields. But holographic thinking suggests that the arrangement of information may be just as fundamental as the things being arranged. Reality may not only be a collection of objects, it may also be a pattern of relationships encoded with astonishing precision. And yet this should not make the world feel less real. A rainbow is not a solid object, but it is real as an optical event. A melody is not stored in any single note, but it is real as a pattern through time. A wave on the ocean is not a separate substance from the water, but it is real as a shape, a motion, a temporary order. In the same gentle way, if space is emergent, that does not erase your life inside it. It only means that the foundation beneath experience may be stranger and more elegant than common sense imagined. The chair beneath you, the air in the room, the quiet weight of your body, and the night sky beyond the window all remain part of the same physical world. The holographic idea does not take them away. It asks us to look more deeply at what it means for them to exist. It suggests that the familiar world may be the surface expression of a hidden structure, the way a calm lake reflects a sky whose depth is not actually inside the water. In this chapter, we are only opening the door. We are not yet trying to solve the mystery. We are simply allowing the possibility to settle, that reality may be real, but not simple, solid, but not fundamental in the way it appears, spacious, but perhaps born from something more abstract than space itself. And there is something peaceful in that thought. The day may have been full of ordinary details, tasks, worries, and small unfinished things, but beneath all of them is a universe patient enough to hold mysteries far larger than the mind can carry at once. For now, you do not need to solve them. You can simply rest inside them, gently, as the strange depth of reality becomes quiet around you. Chapter 2. What a hologram really is. Before the universe can be called holographic in any serious scientific sense, we first need to understand what a real hologram actually is. The word is familiar, but it is often used loosely. In everyday language, people may call almost any floating image a hologram, especially if it looks futuristic or appears to hover in the air. But in physics, a hologram is not just a glowing projection, and it is not simply a clever visual trick. It is a method of recording and reconstructing light in a way that preserves depth. A normal photograph records the brightness and color of light arriving from a scene. When you take a picture of a person, a landscape, or an object on a table, the camera lens focuses light onto a surface. The result is flat, even if the scene itself had depth. You can recognize shapes, shadows, and perspective, but you cannot truly look around the photographed object. The photograph gives you one view, from one angle, at one moment. A hologram works differently. It does not simply capture a focused image. It records a pattern made by light waves. Light behaves as a wave, and like all waves, it has peaks, valleys, direction, and timing. When light reflects from an object, the wave carries information about the object's shape and surface. The returning light is not just bright or dim. It contains subtle timing relationships that tell where different parts of the object were in space. This timing relationship is called phase. You do not need complex mathematics to understand the basic idea. Imagine gentle ripples moving across a pond. Two ripples may rise together, or one may rise while the other dips. When they meet, they can strengthen one another or partly cancel one another. Light waves can do something similar. When waves overlap, they create interference patterns, areas where the combined light becomes brighter or darker depending on how the waves line up. Holography uses this wave behavior. To make a simple optical hologram, a beam of coherent light is split into two parts. Coherent light means that the waves are highly organized and keep a steady relationship with one another. Laser light is especially useful for this because it can provide the kind of ordered wave needed to produce a stable interference pattern. One part of the light shines on the object. After touching the object, it scatters back, carrying information about the object's form. The other part travels directly to the recording surface as a reference beam. When the object light and the reference light meet, they interfere, and the recording surface stores the resulting pattern. To the eye, that stored pattern may not look like the object at all. It may look like a strange set of fine lines, rings, speckles, and cloudy marks. But the surface is not storing an ordinary picture. It is storing instructions for rebuilding the light wave that came from the object. The apparent mess is meaningful because it contains the relationship between the object wave and the reference wave. When the hologram is later illuminated properly, the pattern bends and redirects light. This process is called reconstruction. The light emerging from the hologram can behave as if it had come from the original object. Your eyes receive a wavefront similar to the one they would have received if the object were still there. Because your visual system interprets light direction and depth cues, the reconstructed image can appear three-dimensional. You may shift your head slightly and see the image from a different angle. This is one of the most important differences between a hologram and a photograph. A photograph gives a flat record of brightness from one viewpoint. A hologram can preserve information about how light would travel from many parts of an object into space. It does not only show what the object looked like. It stores a way of recreating the light field associated with the object. That is why a holographic image can have parallax, the slight change in view that happens when you move your head. Parallax is one of the quiet clues your brain uses to sense depth. There is another remarkable feature of holograms that makes them especially useful as an analogy. In an ordinary photograph, each small patch of the image corresponds to a small patch of the scene. If you cut the photograph in half, each half contains only part of the picture. One side may show the person's face, while the other side may show the background. The information is stored in a fairly direct, local way. A piece of the photograph contains a piece of the image. A hologram is more distributed. In many holograms, each part of the recording surface contains information from the whole object, though with reduced detail and clarity. If the hologram is broken, a smaller piece may still reconstruct a view of the entire object, but the image usually becomes dimmer, grainier, or less sharp. This happens because light from many points on the object contributes to many regions of the interference pattern. The information is spread across the surface rather than stored as a simple point-by-point map. This does not mean every fragment of every hologram contains perfect information about everything. Real holograms have limits. They depend on the quality of the recording material, the size of the fragment, the wavelength of light, the viewing geometry, and the amount of information originally captured. But the general idea remains beautiful. The whole can be encoded in a distributed pattern, and depth can be reconstructed from information arranged on a surface. This is where the connection to the cosmic question begins to feel more natural. A hologram shows that a lower dimensional recording can contain the information needed to produce the experience of a higher dimensional image. A flat surface can encode depth. A pattern that looks meaningless can reconstruct a scene. What appears at first to be merely a surface can contain instructions for something that seems to extend beyond it. Still, we must be careful. The universe is not being compared to a cheap stage illusion or a science fiction projector. A physical hologram is made with light, recording material, and optical interference. The holographic principle in theoretical physics is much more abstract. It is not saying that the universe is a literal photograph or that someone is shining a laser through a cosmic plate. The word holographic is used because of the structure of the idea. Information associated with a volume may be described in terms of information on a boundary. This is why the real science of holograms matters. Without understanding the optical version, the cosmic version can sound like fantasy. Once you see what a hologram does, the analogy becomes more disciplined. It is not about unreality, it is about encoding. It is not about deception, it is about how information can be arranged. A holographic image is not the original object, but the light reaching your eyes can carry the correct depth relationships. The appearance of space arises from a pattern. Think again about a small holographic image on a card or glass plate. The surface itself is thin. You can hold it in your hand. Yet when light interacts with it in the right way, an image may appear to occupy depth. Your eyes are not simply fooled by painted shading. They receive structured light that behaves as though it came from different positions. The depth is produced through wave information, not through the physical thickness of the plate. This teaches an important lesson about perception. We do not experience the world directly as raw reality. We experience it through information carried by light, sound, touch, and other signals, then interpreted by the brain. When you see an object across the room, your brain is building a stable experience from light entering your eyes. The object can be real, while your experience of it is still constructed from information. This makes holography a useful bridge between everyday intuition and abstract physics. It gives us a concrete example of something that appears three-dimensional, yet depends on information stored in a different form. It shows that a surface can hold more than a flat image. It shows that what seems like visual depth may be generated from a hidden pattern that is not itself shaped like the thing it produces. When physicists borrow the word hologram for the universe, they are borrowing this idea of encoded depth. They are asking whether space might be less fundamental than the information that describes it. They are asking whether what seems spread through a vast interior might have an equivalent description on a boundary. They are asking whether reality may be organized in a way that is stranger, more efficient and more subtle than ordinary experience suggests. For now, the most important point is simple. A hologram is not just an image that looks three-dimensional. It is a record of wave information. It stores relationships that allow light to be reconstructed. It can make depth appear from a surface, not by magic, but by careful physics. And because of that, it gives us one of the gentlest ways to approach one of the deepest ideas in modern science. So before we imagine the whole universe as holographic, we can rest with the smaller wonder first. A thin surface can hold the memory of depth. A pattern of light and shadow can rebuild the shape of something no longer present. The ordinary world, when looked at carefully, is already full of quiet hints that reality may be more layered than it first appears. And as this idea settles, there is no need to force the mind to hold all of it at once. Let the image remain simple. Light meeting light, waves forming a hidden pattern, depth quietly returning from a surface. The day can loosen now. The room can become still, and the thought of reality as something softly encoded can drift in the background, calm and weightless. Chapter 3: Black Holes and the Mystery of Lost Information. Black holes enter this story because they force physics to ask a surprisingly delicate question. When something falls beyond the reach of the universe, does the universe still remember what it was? A black hole begins with gravity taken to an extreme. It is not a hole in the ordinary sense, and it is not an empty tunnel cut through space. It is a region where so much mass has been compressed into such a small volume that space-time curves inward with overwhelming strength. Far from a black hole, gravity may behave in familiar ways. A star can orbit it, gas can swirl around it, light from nearby matter can still travel outward and reach telescopes. But close enough to the black hole, the rules change. There is a boundary called the event horizon, and beyond that boundary, escape is no longer possible. The event horizon is one of the most important ideas in this chapter. It is not a solid surface. There is no shell, no glass, no material skin wrapped around the black hole. It is a point of no return written into the geometry of space-time. Outside it, a path can still lead away. Inside it, every future path points deeper inward. Even light, which moves at the fastest possible speed in nature, cannot climb back out once it has crossed this boundary. This already makes black holes mysterious. If nothing can escape from inside the event horizon, then the interior is hidden from the outside universe. We can observe the influence of a black hole on nearby stars, gas, and light, but we cannot receive a direct message from within. A black hole is therefore not only a powerful gravitational object, it is also a kind of cosmic veil. It separates what can be known from what cannot be reached. Now imagine that something falls in. It could be a cloud of gas, a burned-out star, a planet, a book, or any object made from matter. Before it falls, that object has details. It has a particular arrangement of atoms. It has shape, temperature, motion, chemical structure, and countless microscopic properties. In physics, those details are part of what we mean by information. Information does not simply mean words written on a page or data stored on a computer. It means the complete physical description of a system, all the details that distinguish one possible state from another. If a book falls into a fire, the words may seem lost, but physics says the process is not truly a disappearance of information at the deepest level. The smoke, ash, heat, and light contain traces of what happened. In practice, it would be hopelessly difficult to reconstruct the book from the final particles and radiation. But in principle, the information is not erased. It has been scrambled into a more complicated form. This principle is especially important in quantum physics. Quantum theory does not allow physical information to simply vanish without a trace. The present state of a closed system should, in principle, contain enough detail to connect with its past. The connection may be unimaginably difficult to decode, but the information is still part of the lawful evolution of the system. This is one of the reasons black holes became so troubling. They seem to take information and hide it permanently. For a long time, black holes were thought of as objects that could only grow. Matter could fall in, energy could fall in, light could cross the event horizon and never return. From the outside, the black hole would become more massive, or spin differently, or perhaps carry electric charge. But many details of what formed it would no longer be visible. A black hole made from a collapsed star and a black hole made from a very different arrangement of matter might look identical from the outside if their large-scale properties matched. This is unsettling because ordinary objects keep traces of their histories. A rock, a tree, a cloud, or a living cell carries structure. If you study it carefully, you can learn something about how it formed. But a black hole appears unusually simple from the outside. It seems to erase the visible differences between the things that created it. The many complicated details of falling matter are reduced, for an outside observer, to a small set of broad properties. Then came the deeper surprise. Black holes may not be completely black. When quantum theory is considered near the event horizon, black holes are expected to emit an extremely faint form of radiation. This is called Hawking radiation. For very large black holes, this radiation would be so weak that it is far beyond ordinary detection. But the theoretical implication is enormous. If a black hole emits radiation, then it can slowly lose energy. If it loses energy, it can slowly lose mass. And if enough time passes, it may eventually evaporate. This creates the information problem in its sharpest form. If matter falls into a black hole, and the black hole later evaporates through radiation, where did the information go? Did it remain locked inside until the end? Did it somehow come out in the radiation? Or did it truly disappear from the universe? At first glance, Hawking radiation seemed to make the problem worse. The radiation appeared to be thermal, meaning that it was described mostly by temperature rather than by the detailed identity of everything that had fallen in. Thermal radiation is like the glow from a hot object. It tells you something about heat, but not necessarily the exact microscopic story of how the object was made. If a black hole evaporated away completely while producing radiation that carried no detailed record of the original matter, then the information would seem to be destroyed. This is the black hole information paradox. It is not just a puzzle about black holes. It is a conflict between the two great pillars of modern physics. General relativity describes gravity as the curvature of space-time and explains why black holes form. Quantum theory describes matter, energy, and information at the deepest known level and tells us that information should not simply be lost. When these two frameworks are applied to black holes, they seem to pull in different directions. The paradox matters because it reveals that our understanding is incomplete. It is not enough to say that black holes are strange. The problem is sharper than that. Black holes sit exactly where gravity, quantum physics, thermodynamics, and information all meet. They are not merely objects in the universe. They are laboratories of thought where the universe exposes the seams between our best theories. Thermodynamics enters through entropy. Entropy is often described as disorder, but in physics, it is more precisely connected to the number of microscopic ways a system can be arranged while still looking the same at a larger scale. A cup of warm tea has entropy because many microscopic arrangements of its molecules can produce the same overall temperature and appearance. A black hole also has entropy, and this was one of the strangest discoveries in theoretical physics. Even though a black hole looks simple from outside, it behaves as if it hides an enormous number of possible internal states. The surprising part is how that entropy is related to the black hole. For ordinary things, entropy usually grows with volume. A larger box of gas can contain more microscopic arrangements than a smaller one. But for a black hole, the entropy is connected to the area of the event horizon. The boundary matters in a way that seems far deeper than expected. The surface that marks the point of no return appears to measure how much information the black hole can contain. This is the clue that leads toward the holographic principle. The event horizon acts like a boundary, and the amount of hidden information seems tied to that boundary rather than to the volume inside. Something about black holes suggests that nature may count information differently when gravity becomes extreme. The interior may not require independent information for every tiny piece of volume in the way ordinary intuition expects. Instead, the boundary may somehow encode the relevant physical content. This does not mean that physicists have solved every detail. The information paradox remains one of the deepest questions in theoretical physics, even though many modern approaches suggest that information is probably preserved. Some ideas propose that Hawking radiation is not perfectly featureless, but contains subtle correlations that carry information outward. Other ideas suggest that our concept of the black hole interior must change. Still others point toward deeper descriptions of space-time, where the inside and outside are related in ways ordinary geometry cannot easily show. What matters for this video is the direction of the clue. Black holes taught physicists that information, gravity, and boundaries are connected. They showed that the edge of a region may carry more meaning than anyone expected. They suggested that the deepest description of space might not be written in the volume itself, but in information associated with its boundary. So the black hole is not just a dark object in space. It is a question made physical. It asks whether the universe can forget. It asks whether information can fall out of reality. It asks whether space has a hidden bookkeeping system more subtle than anything we experience in daily life. And from that question, the holographic idea begins to feel less like fantasy and more like a serious attempt to understand how reality protects its own memory. For now, you can let the paradox remain unresolved. There is no need to carry its full weight. Imagine the event horizon as a quiet border in the dark, not a wall, but a boundary where our familiar ideas begin to fade. Somewhere beyond it, gravity and quantum physics are still waiting to be joined. And here, far from that edge, the night is calm enough to rest inside the mystery. Chapter 4: The Boundary That Holds the Secret. The strange power of the holographic idea begins with a quiet reversal of intuition. Sometimes the edge of a region may know more about the region than the empty depth inside it seems to suggest. In ordinary life, boundaries feel secondary. A wall surrounds a room, but the room itself seems to be the important thing. A box has sides, but we usually care about what is inside the box. A shoreline marks the edge of a lake, but the lake appears to belong to the water stretching across its basin. Our senses tell us that the interior is where reality happens, while the boundary merely outlines it. Physics began to question this intuition through black holes. In the previous chapter, the black hole appeared as a place where gravity hides information behind an event horizon. Now we can look more closely at that horizon, not as a place of destruction, but as a clue. The event horizon is a boundary. It marks the dividing line between events that can still send signals outward and events that cannot. It is not a material surface, and it is not made of atoms. Yet in the mathematics of black holes, it behaves as though it carries deep physical meaning. The surprising discovery is that the amount of entropy associated with a black hole is connected to the area of its horizon. Entropy, in this context, is not simply messiness. It is a measure of how many hidden microscopic arrangements could correspond to the same large-scale object. If many different inner states can produce the same outward appearance, entropy is high. A black hole, although outwardly simple, seems to represent an enormous number of possible hidden states, and the measure of that hidden richness is tied to the size of the boundary, not to the volume that appears to lie behind it. This is difficult because it goes against the way we normally count possibilities. If you have a larger room, you expect it to hold more objects than a smaller room. If you have a larger container, you expect more air molecules, more motions, more possible arrangements. In everyday physics, capacity usually grows with volume. The more space there is, the more ways matter can be arranged inside it. But black holes seem to speak a different language. Their information capacity grows with the surrounding area. To feel why this is so strange, imagine drawing a sphere around a region of space. Common sense says that the deeper volume inside the sphere is where the information lives. Every small part of the interior could contain matter, energy, motion, and fields. If you made the sphere larger, the volume would grow rapidly, and you would expect the possible information inside to grow with it. But gravity places a limit on this thinking. If too much energy is packed into a region, the region can collapse into a black hole. Once that happens, the maximum entropy of that region is not measured like an ordinary gas filling the volume. It is measured by the area of the horizon. This suggests a profound rule. Nature may not allow unlimited information to be stored in a finite region of space. There may be a maximum, and that maximum appears to be related to the boundary surrounding the region. The boundary becomes more than a line between inside and outside. It becomes a kind of accounting surface, a place where the universe seems to keep track of what can be known about the region. The holographic principle grows from this insight. It proposes that the full physical description of a region containing gravity may be expressible in terms of information associated with its boundary. This does not mean that the boundary is a wall covered in symbols. It does not mean that space is painted onto a shell. It means that the number of independent details needed to describe the region may scale like the area of the boundary rather than the volume within it. The word boundary here is mathematical and physical at the same time. It refers to the edge that defines a region, but also to the place where information may be counted. This is a subtle idea, so it helps to separate two things: what we experience and how nature may describe it. we experience a world of depth. We walk through space, cross rooms, look up at the sky, and measure distances between objects. None of that disappears. The holographic principle does not say that the interior is imaginary. Instead, it says that the interior may have an equivalent description in terms of boundary information. In one description, there is a volume filled with fields, particles, light, and gravity. In another description, the same physics may be encoded on a surface surrounding that volume. The word equivalent is important. A map is not the territory, but a good map preserves relationships. A musical score is not the sound of an orchestra, but it can contain the instructions that allow the music to be performed. A genetic sequence is not a living body, but it helps encode instructions used in building and maintaining one. These examples are imperfect, but they show how one form of information can describe something that appears in another form. Holography in physics is far deeper and more precise, but it carries a similar lesson. The form in which information is written may not look like the world it describes. When scientists say the boundary may hold the secret, they are not imagining a literal screen at the edge of the universe with images projected inward. The phrase is more abstract. A boundary can be a mathematical surface enclosing a region. The secret is not a movie projected from outside. It is the possibility that the laws inside the region may be captured by information living on the boundary. The interior and the boundary are not competing realities. They may be two different ways of describing the same underlying physics. This way of thinking changes the role of space. Usually we imagine space first and then place things inside it. First there is a room, then furniture. First there is an arena, then motion. First there is an empty cosmic stage, then stars and galaxies. But holographic thinking hints that space may not be the first ingredient. The relationships that define physical information may be more basic, and what we call space may arise from those relationships. The boundary is important because it shows that depth may be reconstructed from fewer independent ingredients than intuition expects. This does not make the idea easy to prove in our own universe. The clearest mathematical examples of holography work in special theoretical settings, not in a simple copy of the universe we observe around us. Our universe is expanding, filled with matter and radiation, shaped by dark energy, and still not fully understood. Scientists therefore use holography carefully as a principle, a clue, and a powerful tool, rather than as a finished description of everything. But even as a clue, it is remarkable. It says that black holes are not isolated oddities. They may be pointing toward a general truth about gravity and information. The boundary also helps soften one of the deepest fears raised by black holes, the fear that information simply vanishes. If the boundary of a black hole carries information in some form, then the event horizon is not merely a curtain of ignorance. It may be part of the universe's bookkeeping. It may encode what has fallen in, not in any ordinary readable way, but in the deeper language of quantum gravity. This possibility does not yet give a simple picture of exactly how information escapes or is preserved, but it changes the question. Instead of asking where the information went, we begin to ask how it was encoded. This is why the boundary feels almost poetic, even inside rigorous physics. A line that seemed to mark loss becomes a place of preservation. A surface that seemed passive becomes active in the deepest description. The edge of a black hole, once imagined only as a point of no return, becomes a clue that nature may store reality differently from the way we experience it. And perhaps that is the gentlest way to understand this chapter. The universe may not waste information. It may not need to fill every piece of volume with independent detail in the way our minds expect. It may weave the story of a region into its boundary, like a quiet record of what the interior can become. The secret is not that the inside is unreal. The secret is that the inside and the edge may be more intimately connected than ordinary space reveals. For now, let the image remain simple. A boundary surrounds a darkness. The darkness seems silent, but the boundary is not empty. It carries a hint, a measure, a hidden order. And as the day begins to fade from attention, you can rest with that image, the universe holding its secrets gently at the edge of what can be seen. Chapter 5. Why space itself may be built from information. To understand why the holographic idea is so powerful, we have to consider a possibility that feels almost impossible at first. Space may not be the container of reality, but something reality produces. Most of us imagine space as the most basic thing there is. Before anything can happen, there must be somewhere for it to happen. Before a planet can orbit a star, there must be distance between them. Before light can travel, there must be a path for it to cross. Space feels like the quiet background of everything, the empty stage on which matter moves, fields spread, and time passes. But modern physics has slowly made that simple picture less certain. Space no longer looks like a passive emptiness. In relativity, space and time are linked into a flexible structure that can curve, stretch, and respond to matter and energy. Gravity is not only a pull between objects, it is also the way objects move through curved space-time. A planet follows a path shaped by the sun because the geometry around the sun has changed. The stage is not still. The stage participates. Quantum physics adds a different challenge. At the smallest known scales, nature is not described mainly by little objects sitting in definite places. It is described by states, probabilities, interactions, and correlations. What matters is not only where something is, but how it is related to other things, what can be measured, and what information is available about the system. The deeper we go, the less reality looks like tiny furniture arranged inside a pre-built room. It begins to look more like a network of possible relationships. This is where information becomes central. In physics, information does not mean gossip, opinion, or a message written in human language. It means the physical distinctions that make one state different from another. If a particle has one possible arrangement rather than another, that difference is information. If a system can be described in more than one possible way, the details that select its actual state are information. Information is not floating outside nature. It is part of how physical systems are described. A simple example is a coin lying on a table. If you know which side faces upward, you have information about the coin. A more complex example is a gas in a room. To describe it fully, you would need to know the positions and motions of all its molecules, which is far beyond ordinary human ability. Yet that enormous hidden detail gives rise to simple large-scale properties such as temperature and pressure. The everyday feeling of warm air is real, but it emerges from microscopic information that your senses do not track directly. Space may be similar in spirit, though far more profound. What if distance is not basic? What if the sense that one object is here and another object is far away arises from a deeper informational structure? In that view, space would not be the first ingredient. It would be an organized result, a way that information arranges itself into geometry. This idea may sound abstract, but science already knows many cases where familiar properties emerge from hidden organization. Wetness is not a property of a single water molecule. It appears when many molecules interact together. Sound is not a thing separate from matter. It is a pattern of pressure moving through air, water, or another medium. A crystal's shape is not imposed from outside. It emerges from the repeated arrangement of atoms. In each case, the larger experience is real, but it is built from a deeper pattern. Emergence does not mean illusion. It means that a property becomes meaningful at one level, even though it is not fundamental at another. A wave on the ocean is real enough to rock a boat, but it is not made of a special substance called wave. It is water behaving in a coordinated way. Likewise, if space is emergent, it would still be real enough to hold stars, galaxies, bodies, and rooms. The point would be that space is not the deepest layer. It may be the large-scale expression of something more basic. The holographic principle gives this possibility a strong reason to be taken seriously. Black holes suggest that the amount of information contained in a region with gravity may be limited by a boundary rather than by ordinary volume. That is already strange. But the larger lesson is even stranger. Geometry and information may be two sides of the same description. The shape of space may not be separate from the information needed to describe what space contains. This is one of the most important shifts in modern theoretical physics. For a long time, people imagined that matter lives inside space. Then relativity showed that matter and energy affect the shape of space-time. Now, holographic thinking suggests something deeper still. Space-time itself may arise from quantum information. The container may come from the contents, or more carefully, from the relationships that organize the contents. One reason this idea has become so influential is that certain mathematical models show a surprising connection between gravitational space and quantum systems without gravity. In these models, a universe with gravity inside a volume can be described by a quantum theory on a boundary. The two descriptions are not merely similar in mood, they can match in precise ways. A question about geometry in one description can become a question about information in another. This does not prove that our own universe works exactly like those models, but it reveals that space can, at least in principle, emerge from a non-spatial quantum description. The word non-spatial is important. It does not mean unreal. It means that the deeper description may not begin with distance in the ordinary sense. Instead of saying that two things are near because they are separated by a small amount of space, the deeper theory might say they are near because their quantum information is strongly related. Things that are weakly related may appear far apart. In this view, distance could be a reflection of pattern, connection, and correlation. This is not how we experience the world. We experience space directly. We cross a room by walking. We look at the moon and see it as distant. We watch shadows move and feel time passing. But human experience is built for survival at ordinary scales, not for revealing the deepest structure of physics. Our senses evolved to navigate surfaces, bodies, food, weather, danger, and motion. They were never meant to show whether geometry itself is fundamental. The idea that space may be built from information also changes how we think about emptiness. Empty space does not seem empty in modern physics. Fields fill the universe. Quantum fluctuations occur even in what we call vacuum. Gravity can ripple through space-time. Dark energy appears connected to the large-scale behavior of space itself, though its nature remains uncertain. The vacuum is not a simple nothing. It has structure, laws, and physical consequences. If space is informational, then emptiness may be less like a blank stage and more like a quiet state of an underlying system. The absence of visible objects would not mean the absence of reality. It would mean that the deeper structure is arranged in a way that appears calm at large scales. Just as a still lake contains molecules in constant motion, empty space may hide activity beneath its smooth appearance. This perspective also helps explain why physicists speak of reality in terms of laws and states, rather than only objects. An object is not just a thing sitting somewhere. It is a stable pattern in fields and information. An electron, for example, is not a tiny ball with a definite surface. It is an excitation of a quantum field, described by properties and interactions. A star is not only a glowing sphere. It is a gravitational, nuclear, thermal, and electromagnetic system held together by balances that can be described physically. Everything we call a thing is also a pattern. If space itself is part of the pattern, then the universe becomes less like a warehouse filled with objects and more like a vast relational structure. The distances, shapes, and paths we observe would be the way this structure appears from within. We would not stand outside it and inspect it from beyond. We are part of it. Our bodies, brains, memories, and measurements all belong to the same informational fabric. It is important, again, not to overstate what is known. Scientists have not completed a final theory showing exactly how the space of our universe emerges from information. The idea is powerful, but still under development. It belongs to the frontier where quantum mechanics, gravity, thermodynamics, and cosmology meet. Some parts are well supported in special theoretical settings. Other parts remain open questions. The honesty of science is that it can hold a beautiful idea without pretending every detail is settled. Still, even as an unfinished idea, it points in a fascinating direction. Space may be less like a thing and more like a relationship. Distance may be less like an absolute background and more like a measure of connection. Geometry may not simply contain information. It may be made from information. And if that is true, then the universe is not only vast, it is deeply encoded. For now, let that thought become quiet rather than overwhelming. The room around you may feel simple, but beneath its stillness may be layers of structure too subtle to see. The space between you and the stars may not be empty distance alone, but the visible shape of hidden order. You do not need to solve that order tonight. You can rest inside it, gently, as if space itself were holding you in a calm pattern of information. Chapter 6. The universe is a projection, not an illusion. When people first hear that the universe might be holographic, it is easy to imagine something false like a stage trick, a dream, or a picture pretending to be a world. But that is not what the scientific idea means. If the universe can be described holographically, the point is not that reality is fake. The point is that reality may have more than one valid description, and the familiar description we live inside may not be the deepest one. The word projection can be misleading if we take it too literally. In everyday language, a projection is often an image cast onto a wall or screen. It depends on something outside it, such as a lamp, a lens, or a machine. The image can vanish when the machine is turned off. It may look convincing, but it has no weight of its own. This is not the right way to think about the universe. No serious version of the holographic idea requires a cosmic projector shining stars, planets, and people into existence. A better way to understand projection is as a relationship between descriptions. Sometimes the same physical reality can be described in two different languages. One description may use space, distance, gravity, and objects moving through a volume. Another may use information, quantum states, and relationships written on a boundary. If both descriptions lead to the same physical predictions, then neither is simply fake. They are different windows into the same underlying structure. Science already works this way in many ordinary cases. A wave in water can be described as a moving shape on the surface, but it can also be described in terms of the motion of countless water molecules. The wave is real. It can carry energy, rock a boat, and break against a shore. Yet the wave is not a separate substance floating above the water. It is a pattern that appears when the water behaves collectively. Calling the wave emergent does not make it unreal. It helps us understand what kind of reality it has. Temperature offers another quiet example. You can feel warmth on your skin without knowing the microscopic motion beneath it. A warm room is real in the way you experience it. Still, at a deeper level, temperature comes from the statistical behavior of many particles. The warmth is not an illusion, even though it is not fundamental in the same way as the individual motions that give rise to it. It is a real feature of the world at the scale where bodies, rooms, and weather exist. The holographic view asks us to treat space in a similar spirit. Perhaps the depth we move through is not fake, but emergent. Perhaps the distances between things are real for beings like us, while also arising from a deeper informational description. This is a difficult shift because space feels more basic than temperature or waves. It feels like the condition for everything else. But physics has already shown that what feels basic to human experience is not always basic to nature. This is why the phrase "not an illusion" matters. An illusion is something that misleads us about what is there. A mirage on a hot road looks like water, but there is no pool waiting on the pavement. A shadow may look like a moving creature, even though it is only a change in light. In such cases, perception gives us a false object. The holographic idea is different. It does not say that tables, planets, or galaxies are false objects. It says the way their existence is encoded may be more subtle than ordinary intuition suggests. If you place your hand on a table, the table resists your touch. That resistance is physical. It comes from electromagnetic interactions between the atoms in your hand and the atoms in the table. The table has mass, structure, and stability. Its reality does not disappear because its deepest description may involve fields, quantum states, or information. In the same way, if the universe is holographic, the chair beneath you, the air around you, and the stars outside the window remain part of the lawful physical world. The idea becomes less strange when we remember that human experience is always mediated. You never see an object by touching its ultimate essence. You receive light that has interacted with it. Your eyes convert that light into signals. Your brain organizes those signals into color, shape, motion, and depth. This does not mean the object is imaginary. It means your experience of the object is a constructed representation of a real physical process. Perception is not a lie simply because it is built from information. In physics, descriptions are also representations. A map represents a landscape, but the map is not the landscape. A map may flatten mountains, shrink distances, and use symbols instead of trees and rivers. Still, a good map preserves relationships that matter. It can guide a traveler through real terrain. A different kind of map might show climate, roads, political borders, or elevation. Each map leaves out something and emphasizes something else. The land remains real, while its descriptions vary. The same can be true at a far deeper level. A gravitational description may speak in the language of curved space-time. A quantum description may speak in the language of states and correlations. A holographic relationship suggests that, in some cases, these languages may describe the same physics from different angles. The projection is not a trick image. It is a translation between ways of representing reality. This is one reason scientists use the word duality. A duality is a relationship where two theories that look very different turn out to be equivalent in what they predict. One side may be easier for certain questions, while the other side may be easier for different questions. It is like discovering that two very different stories have the same plot beneath them, or that two musical arrangements carry the same melody in different instruments. The forms differ, but the underlying content matches. In holographic theories, the interior world with gravity can sometimes be related to a boundary theory without gravity. That sounds extraordinary, and it is. But the key lesson is not that one side is real and the other side is false. The lesson is that reality may be flexible in how it can be described. What appears as geometry in one language can appear as information in another. What appears as depth in one description can arise from relationships in another. This helps protect the idea from a common misunderstanding. Saying the universe might be holographic is not the same as saying it is a simulation. A simulation usually means a system running inside some external machine, built by something outside the simulated world. The holographic principle does not require that. It does not require programmers, hardware, or a hidden computer beyond the cosmos. It is a proposal about the structure of physical law, not a claim about artificial design. It is also not the same as saying consciousness creates the universe. The holographic idea does not depend on human minds looking at things in order to make them exist. Stars burned long before anyone could see them. Galaxies formed through gravity, gas, radiation, and dark matter over cosmic time. The physical universe behaves according to laws, whether or not human beings are present. Holography is about how those laws may be organized, not about reality waiting for attention. So what would projection mean, if not illusion, simulation, or mind-made reality? It would mean that the world we experience as spacious may be the large-scale appearance of a deeper structure. The familiar description in terms of three-dimensional space may be like a surface pattern translated into depth, or like a complex melody emerging from silent notation. The experience is real, but the source of its order may lie in a form we do not directly perceive. This gives the idea a quiet dignity. It does not tear the world away from us. It deepens it. It says that the ordinary room, the distant galaxy, the falling rain, and the body breathing calmly in the dark may all belong to a reality whose structure is more elegant than it first appears. The universe may be projected in the sense that depth arises from a deeper code of relationships, but the projection is still the universe. It is still physical, stable, measurable, and shared. There is comfort in that. Strange physics does not have to make the world fragile. It can make it richer. The more deeply science looks, the more it often finds that familiar things are supported by hidden order, matter by fields, heat by motion, gravity by geometry, and perhaps space by information. The everyday world remains, but it gains another layer beneath it. For now, let the word projection become gentle rather than unsettling. It does not mean your life is weightless or false. It means the reality holding you may be written in a language deeper than ordinary sight. The day can soften around that thought. The room is still real, the night is still quiet, and you can let yourself rest inside a universe that may be stranger than it seems, but not less true. Chapter 7: Quantum Entanglement and the Hidden Threads of Reality. If the holographic universe has a hidden language, quantum entanglement may be one of the first places where that language becomes visible. Entanglement is one of the strangest and most important features of quantum physics. It is also one of the easiest to misunderstand. In popular descriptions, it is sometimes made to sound like magic, telepathy, or a secret signal passing instantly across space. But the real science is subtler and more interesting. Entanglement is not a message traveling faster than light. It is a kind of shared quantum description, where two or more systems cannot be fully understood as separate things, even when they are far apart. To see why this matters, begin with a simple comparison. In ordinary life, two objects can be correlated because they share a history. If you have a pair of gloves and place one glove in one box and the other glove in another box, then send the boxes to different cities. Opening one box tells you something about the other. If you find the left glove, you immediately know the other box contains the right glove. Nothing mysterious travels between the boxes. The information was already settled when the gloves were packed. Quantum entanglement is different. In an entangled system, the connection is not simply a matter of hidden ordinary properties waiting to be revealed. The quantum state describes the combined system as a whole. Before measurement, the parts do not always have separate, fully defined properties of the kind we expect from everyday objects. When measurements are made, the results can show correlations stronger than classical common sense allows. Experiments have repeatedly confirmed that nature behaves this way. This does not mean that entanglement lets us send usable messages instantly. That point is important. The outcomes of individual quantum measurements still contain unavoidable randomness. Even if two systems are entangled, a person measuring one side cannot choose a result and force a readable message to appear on the other side. The correlations become clear only when measurement results are later compared through ordinary communication. So entanglement is deeply non-classical, but it does not break the usual rule that information signals cannot travel faster than light. What entanglement reveals is not a shortcut for communication, but a deeper kind of relationship. It tells us that quantum systems can share a state that belongs to the whole rather than to the pieces separately. The parts may be distant in ordinary space, yet the complete description refuses to treat them as fully independent. This is why entanglement is often described as one of the defining features of quantum theory. It is not a small decoration added to the theory, it is part of the structure. In the context of a holographic universe, entanglement becomes especially important because it may help explain how space itself is organized. Earlier, we considered the possibility that space is not the first layer of reality, but something that emerges from information. Entanglement gives that idea a physical shape. It suggests that the pattern of quantum connections between parts of a system may help determine what we experience as geometry. This is a profound shift. Usually, we imagine that two things are related because they are close together in space. A cup is near your hand because the distance between them is small. The moon is far away because the distance between Earth and the moon is large. Space comes first, and relationships are arranged inside it. But in some modern approaches to quantum gravity, the order may be partly reversed. The relationships may come first, and spatial distance may arise from the pattern of those relationships. In this view, closeness would not only mean being near in a pre-existing arena. It could mean being strongly connected in the underlying quantum information. Separation would not only mean empty distance. It could mean weaker connection, fewer shared correlations, or a different pattern of entanglement. Geometry would become a readable expression of hidden quantum structure. This idea is still under development, and it must be treated carefully. Scientists have not completed a final theory of quantum gravity. No one can yet point to the night sky and say with certainty that every distance is built from entanglement in exactly this way. But in several powerful theoretical models, entanglement and geometry are connected with surprising precision. Change the entanglement pattern, and the shape of the corresponding space can change. Reduce certain connections, and a smooth region may separate into pieces. Increase the right kind of connection, and what looks like connected space may become possible. This is why entanglement is sometimes imagined as the hidden stitching of reality. The phrase is poetic, but the idea behind it is mathematical. It does not mean there are literal threads stretched between stars. It means that the physical relationships described by quantum information may underlie what appears to us as continuous space. Just as a fabric looks smooth from far away but is made from interwoven strands, space-time may look smooth at ordinary scales while arising from a deeper pattern of quantum relations. The connection with holography is natural. In holographic theories, a gravitational world can have an equivalent description in a lower dimensional quantum system. The geometry of the gravitational world is not independent from the information in the quantum description. Entanglement in that quantum system can correspond to features of the emergent space. In simple language, the way information is shared helps shape the way space appears. This is very different from thinking of space as an empty container. It suggests that space is more like a network of meaningful relations. The distance between things may not be an isolated fact. It may be part of a larger informational pattern. The smoothness of space may depend on the right arrangement of quantum correlations. The continuity of the world around us may be something maintained by hidden order. There is a useful everyday analogy, though it is only an analogy. Think of a social network. Two people may live in different cities, but be closely connected through shared friends, shared history, and frequent communication. Two other people may live on the same street, but have no meaningful connection at all. In the social network, nearness is not defined only by physical distance. It is defined by relationships. Quantum entanglement is not social connection, of course, and it is governed by precise physical laws rather than human choices. But the analogy helps loosen the idea that distance must always be the most basic measure of closeness. Another helpful image is a woven carpet. From above, you see patterns, colors, and shapes. The design may look continuous, but beneath the surface, The image depends on knots and threads crossing in specific ways. If the hidden weave changes, the visible pattern changes. The holographic view suggests something similar, but at the deepest level of physics. The world of space and gravity may be the visible pattern, while quantum information supplies the hidden weave. Entanglement also changes how we think about separation. In everyday life, distance often feels like independence. If something is far away, it seems disconnected from us. But quantum physics shows that separation in space does not always mean complete separateness in description. Systems can be distant and still belong to one shared quantum state. This does not make the universe mystical, it makes it relational. It reminds us that physical reality may be defined not only by objects, but by the lawful connections between them. This is especially important for black holes. When matter falls into a black hole and radiation slowly comes out, entanglement becomes part of the question of whether information is preserved. The radiation, the black hole, and the fields around it may be linked in subtle quantum ways. Understanding those links is part of understanding whether the universe keeps its memory. In this sense, entanglement is not only a curiosity of small particles, it reaches into the deepest questions about gravity, horizons, and the fate of information. Still, we should not confuse depth with certainty. Entanglement is real and experimentally confirmed. Its role in quantum technologies is practical and measurable. Its possible role in building space-time is more theoretical, though strongly motivated by modern research. That distinction matters. Good science can be both imaginative and careful. It can follow a beautiful clue without pretending the final answer has already been reached. What makes entanglement so powerful for this story is that it gives information a kind of physical intimacy. It shows that the universe is not merely made of separate parts placed side by side. At the quantum level, the description of the whole can be more fundamental than the description of the pieces. And if space itself emerges from such descriptions, then reality may be woven from connection before it is spread into distance. The hidden threads of reality are not threads you could touch. They are not glowing lines in the dark. They are relationships, correlations, and shared quantum states written into the behavior of nature itself. They may help explain why space has shape, why regions are connected, and why the universe can appear smooth and continuous even if its deepest structure is informational. For now, it is enough to rest with the gentlest version of the idea. The universe may not be a collection of lonely things floating in emptiness. It may be a vast pattern of relationships, some visible, many hidden, all contributing to the calm appearance of space. And as the day loosens its grip, you can imagine those hidden connections becoming quiet around you, not pulling you anywhere, not asking anything from you, simply holding the world together while you rest. Chapter 8. Could our three-dimensional world come from a deeper surface? The boldest form of the holographic idea asks us to imagine that the depth of our world may not be the starting point of reality, but something that can arise from information written in a more hidden way. This sounds impossible at first because depth feels so immediate. You can move forward and backward. You can lift your hand above a table. You can look across a room and sense the distance between your eyes and the far wall. The world does not feel like a flat surface. It feels open, spacious, and filled with directions. There is height, width, and depth, and every ordinary action depends on them. Walking, reaching, looking, breathing, and turning your head all seem to confirm that space has volume. So when physicists ask whether a three-dimensional world could come from a deeper surface, they are not denying the reality of your experience. They are asking a more careful question. Could the full description of a world with depth be equivalent to a description that uses fewer spatial dimensions? Could the physics inside a volume be captured by information living on a boundary? Could what appears as an interior, with distances and directions, be another way of reading a pattern that does not begin as an interior at all? To approach this, we first need to loosen the word surface. In everyday life, a surface is something you can touch, like the top of a table, the skin of a balloon, or the face of a mirror. But in physics, a surface can also mean a boundary in a mathematical sense. It can define the edge of a region, the limit where one description ends, or the place where information is assigned. It does not have to be a solid shell floating somewhere in space. It can be a way of organizing a theory. A simple example is the surface of a sphere. The surface itself has only directions along it. You can move north, south, east, or west across it, but if you are restricted to the surface, you do not move inward or outward through the sphere. The full ball has volume, but the surface has one fewer spatial dimension than the ball it encloses. This difference between surface and volume gives us a useful mental image, though the real holographic idea is much more subtle. In holographic theories, the surface is not just a container wrapped around a normal interior. The astonishing claim is that the surface description may contain everything needed to describe the interior physics. What looks like a higher dimensional world with gravity can, in certain theoretical settings, be equivalent to a lower dimensional quantum system without gravity. The interior is not copied crudely onto the surface. Instead, the two descriptions match in a deep way. One speaks the language of curved space and gravity. The other speaks the language of quantum information and fields. Yet they can describe the same physical content. This is why the idea is so powerful. It suggests that depth may be a translation. What one description calls distance into the interior, another description may represent as a scale, pattern, or organization of quantum information. The extra direction, the one that makes a lower dimensional description appear to become a higher dimensional world, may emerge from how the information is arranged. One way to picture this gently is to think about resolution. When you look at a digital image from far away, you see shapes and depth cues. When you zoom in, you see smaller patterns and structure. The image changes with scale. In some holographic ideas, the direction into the emergent interior is related to the scale at which the boundary system is being described. The deeper you move in the gravitational picture, the more the description relates to larger, smoother patterns in the boundary theory. This is only an analogy, but it helps show how an apparent spatial direction might arise from something that is not simply another ordinary direction on a surface. This does not mean our universe is literally painted on a distant wall. There is no known physical screen at the edge of the cosmos where every person, planet, and galaxy is drawn. The boundary in holography is not a movie screen. It is a place in the structure of a theory where information can be defined. The surface may be extremely abstract, and in some models it lies at an infinite edge of a particular kind of space-time. It is not something a spacecraft could simply fly toward and touch. The best understood examples of holography involve idealized universes with special geometry. These models are not exact copies of the universe we observe. Our universe expands, contains dark energy, and appears to have a different large-scale structure from the simplest holographic examples. That matters. Scientific honesty requires saying that holography is not yet a finished explanation of our actual cosmos. It is a powerful principle, a mathematical discovery, and a guide toward quantum gravity, but not a settled picture of the night sky above us. Still, idealized models can teach real lessons. Physics often advances by studying simplified worlds where the equations become clearer. A frictionless surface is not found perfectly in nature, but it helps reveal the laws of motion. An ideal gas is not a perfect description of every gas, but it teaches the relationship between pressure, temperature, and molecular motion. In the same way, holographic models may not be our universe exactly, yet they reveal something profound about how gravity and quantum information can fit together. The central lesson is that dimensions may not be as fundamental as they seem. We usually count dimensions as basic facts. A line has length, a surface has area, and a volume has depth. But holography suggests that the number of apparent dimensions in a gravitational world may depend on the way information is organized. A higher dimensional space may emerge from a lower dimensional system when the relationships inside that system are rich enough. This idea also changes how we think about boundaries. A boundary is often treated as less important than the thing it surrounds. But in holography, the boundary description can be complete. It may not merely summarize the interior, it may define it. The interior is then not a separate object hidden behind the surface, but a different expression of the same underlying information. The surface and the depth are linked so deeply that asking which one is more real may be the wrong question. They may be two ways of reading the same physical truth. This is difficult because our minds are built to imagine objects in space, not space as something that needs explanation. We imagine a surface here, an interior there, and a viewer standing outside both. But with the universe, there may be no outside viewpoint. We are not observers looking at reality from beyond its boundary. We are part of the very structure being described. If our world has a holographic description, then we live inside one side of that description. We experience the emergent depth from within. The phrase deeper surface sounds almost contradictory, and that is part of its beauty. A surface usually feels shallow. Depth feels richer. Yet the surface in holography may be deeper in the explanatory sense, because it may contain the information from which depth itself arises. It is not deeper by being farther inward. It is deeper by being more fundamental in the description. The same kind of reversal appears in other parts of science. The color of an object feels like a direct property, but it depends on wavelengths of light, surface interactions, and perception. The solidity of matter feels simple, but it arises from quantum fields and electromagnetic forces. The flow of time feels obvious, but it is tied to entropy, motion, and space-time. Again and again, what seems immediate turns out to be a higher-level appearance built on quieter rules. If the three-dimensional world comes from a deeper surface, then depth is not destroyed. It is explained differently. The distance between stars, the shape of galaxies, the motion of planets, and the quiet space inside a room would still behave according to physical law. But the reason space has that behavior might come from a more basic encoding. The world would be like a story that can be told in two languages. One language of geometry, another language of information. Each language would reveal something the other hides. This also makes the holographic idea less frightening. It is not a claim that your body is flat, or that the universe is only a picture, or that everything is trapped on a surface like paint. The claim is subtler and more elegant. It says that the full richness of a world with depth may be describable through information organized with fewer dimensions. The depth is real as experience and as physics. It may simply not be fundamental in the way it appears. For now, we can let the question remain open. Could our three-dimensional world come from a deeper surface? Perhaps not in the simplest way. Perhaps the real universe requires a more complex form of holography than current models provide. But the possibility itself has changed physics. It has shown that space, gravity, information, and quantum theory may be connected more intimately than anyone once imagined. And as you rest with that thought, there is no need to picture the whole universe at once. Let the idea become quiet and simple, a surface that is not merely a surface, a depth that may arise from hidden order, a world that remains real, even if its roots are stranger than sight can follow. The night can hold that mystery gently, while the mind releases the day and settles into stillness. Chapter 9. Can we ever test the holographic universe? The most important question now is not whether the holographic universe sounds beautiful, but whether science can ever place the idea under the pressure of evidence. A scientific idea becomes stronger when it does more than inspire imagination. It must connect to observation, calculation, and prediction. It must tell us something definite enough that nature can answer back. This is what makes the holographic universe such a fascinating challenge. The idea is deep, elegant, and mathematically powerful, but testing it in the universe we actually inhabit is not simple. It lives near the border between what we can measure directly and what our theories suggest must be true if gravity and quantum physics are to fit together. The first difficulty is scale. Holographic ideas are connected to quantum gravity, and quantum gravity becomes most important in places where gravity is extremely strong or distances are unimaginably small. Everyday space is smooth and calm. A room does not reveal its deepest structure when you walk across it. A beam of light traveling through the air does not obviously show whether space-time is made from information. If space has a microscopic structure, that structure is expected to appear far below the scale of atoms, far below anything ordinary instruments can easily reach. This does not mean the idea is unscientific. Many important scientific ideas are first tested indirectly. Atoms were accepted before anyone could see them in the everyday sense because they explain chemistry, heat, and the behavior of gases. The interior of the sun cannot be visited, but its structure is tested through light, particles, sound waves inside the sun, and models of nuclear fusion. In science, direct seeing is not the only path to knowledge. A theory can be tested by whether its consequences match the world. For holography, one path of testing is mathematical consistency. That may sound weaker than observation, but in fundamental physics, it matters enormously. If a proposed theory of gravity and quantum mechanics produces contradictions, it cannot describe nature. If two very different descriptions give the same answers in carefully studied cases, that can reveal a real structural truth. Some holographic models show that a world with gravity can be equivalent to a quantum theory described on a boundary. These models are not exact copies of our universe, but they demonstrate that holography is not merely a metaphor. it can be made precise. Still, mathematical success is not the same as final proof. A model can be useful without being literally our universe. The most famous holographic examples work best in special kinds of space-time, with geometry unlike the large-scale universe we observe. Our cosmos expands. It contains galaxies, dark matter, radiation, and dark energy. Its distant future and boundary structure are more complicated. So the question becomes careful. Can the lessons from idealized holographic models be extended to a universe like ours? Another possible route is through black holes. Black holes are real astronomical objects, and they are places where gravity becomes intense enough to expose deep questions about information. Observations of stars orbiting compact dark objects, gravitational waves from black hole mergers, and images of glowing material around black holes all test our understanding of strong gravity. So far, these observations agree very well with the predictions of general relativity in the situations we can observe. But they do not yet reveal the microscopic quantum structure of an event horizon. They show that black holes behave like the theory expects at large scales, not exactly how information is preserved at the deepest level. The information problem remains harder to test directly. The radiation expected from large astrophysical black holes is far too faint compared with other cosmic backgrounds. A black hole made from a star would emit an extremely weak quantum glow, overwhelmed by warmer radiation in the universe around it. The full evaporation of such a black hole would take an unimaginable amount of time. This means that the cleanest version of the information question cannot simply be watched with a telescope. Nature hides the crucial process behind scale, faintness, and time. There have also been attempts to search for possible signs that space-time is not perfectly smooth. One idea proposed that if space has a holographic kind of microscopic uncertainty, it might produce an incredibly tiny noise in precision instruments. Experiments using interferometers have looked for certain forms of this possible noise by comparing the paths of light with extreme sensitivity. The important result is careful but limited. Particular models of measurable holographic noise have not been supported by those experiments. That does not rule out the holographic principle as a whole. It only tells us that nature did not show that specific signal in that specific way. This distinction is essential. A failed test of one predicted effect is not a failure of every related idea. Holography is a broad principle, not a single simple mechanism. Some popular versions imagine space-time as pixelated or jittering in a direct, measurable way. But the deeper theoretical idea does not necessarily require such crude effects. The absence of one kind of noise does not mean that space cannot emerge from information. It means the universe is subtler than that proposed signal. Cosmology offers another possible window. If the early universe was once extremely hot, dense, and quantum in character, perhaps traces of holographic structure could appear in the large-scale distribution of matter or in the ancient light left from the early cosmos. Some researchers have explored whether holographic models can reproduce features of the observed universe. This is interesting, but also difficult. Many different models can sometimes fit broad cosmological patterns. A successful fit is not automatically unique proof. To become truly convincing, a holographic model would need to make predictions that are both distinctive and accurately confirmed. This is one of the central challenges in testing deep theories. The universe gives us data, but the data can often be interpreted in more than one way. A curve on a graph may support several models. A pattern in ancient light may be explained by different assumptions about the early universe. A mathematical theory may be elegant, but elegance alone is not evidence. Science has to ask whether a theory risks being wrong. The more precisely a theory can say what should or should not happen, the more strongly it can be tested. There are also laboratory systems that imitate some features of holographic ideas. Quantum computers and carefully controlled quantum systems can be used to study models where information, entanglement, and geometry have a relationship. These experiments do not create real cosmic wormholes or miniature universes in the ordinary sense. They test simplified quantum systems whose mathematics resembles certain gravitational problems. They are valuable because they make abstract ideas more concrete, but they are not direct evidence that our universe is holographic. They are more like wind tunnels for theory, controlled settings where parts of a larger idea can be explored. So can we ever test the holographic universe? The honest answer is yes, but probably not in one simple dramatic experiment. There may never be a single machine that lights up and announces that reality is holographic. Instead, evidence would likely accumulate from several directions. Better theories of quantum gravity, deeper understanding of black holes, more precise cosmological observations, quantum simulations, and perhaps unexpected experimental clues about space-time itself. The test may be a convergence rather than a moment. This is common in mature science. The evidence for a major idea often becomes strong because many separate lines begin to point the same way. No single observation carries the whole burden. The theory becomes trusted because it explains more, predicts better, avoids contradictions, and connects phenomena that once seemed separate. Holography may follow this path if it is part of the true structure of nature. At the same time, it may turn out that the holographic principle is not the final description of our universe. It may be a clue, a partial truth, or a powerful tool that works in some settings but must be transformed for our cosmos. That wouldn't make it a failure. In physics, even incomplete ideas can open doors. They can show which questions matter, which assumptions are fragile, and which hidden connections deserve attention. The most grounded way to hold the idea is with patience. Holography is not proven as a complete description of the universe around us. It is also not empty speculation. It is a serious scientific framework born from black holes, quantum theory, gravity, and information. Its testability is difficult, but not hopeless. Its meaning is uncertain, but not vague. It stands in that rare place where mathematics, observation, and imagination all meet, each one correcting the others. For now, the universe keeps its answer quiet. Telescopes watch black holes from afar, detectors listen for ripples in space-time, laboratories guide light along delicate paths. Quantum systems are arranged, measured, and compared. Piece by piece, science asks whether depth is fundamental or whether it rises from information more hidden than space itself. And there is calm in that slow asking. We do not need the final answer tonight. The mystery can remain open without becoming heavy. The world outside the window is still steady, the stars are still distant, and the mind can rest while science continues, gently and patiently, to ask reality what it is. Chapter 10. If reality is holographic, what does that mean for us? If reality is holographic, the most important meaning is not that the world becomes less real, but that reality may be deeper, more layered, and more carefully organized than ordinary experience can reveal. After traveling through this idea, it can be tempting to ask what changes for a human life. If space may emerge from information, if black holes hint that boundaries can encode what happens inside, and if entanglement may help shape the geometry of the world, then what does any of that mean for the person sitting quietly under a night sky, breathing in an ordinary room, living through an ordinary day? The first answer is simple and important. Daily life does not dissolve. A holographic description would not make the world disappear. It would not make your body imaginary, or your memories meaningless, or the stars outside less physical. Science often changes the explanation beneath experience without destroying the experience itself. When people learned that Earth moves around the sunrise did not stop being beautiful. When matter was understood as atoms and fields, a stone did not stop feeling solid. When time became part of space-time, clocks did not stop working. Deeper explanations do not erase the world. They reveal how the world is held together. If holography is part of the truth, then space may be one of those familiar things whose foundation is stranger than its appearance. We experience space as the place where life happens. We move through it, build homes inside it, look across it, and measure it. But at a deeper level, space may be connected to information, entropy, quantum relationships, and boundaries. This would mean that what feels like empty distance may have structure. The silence between galaxies may not be a meaningless void, but the visible expression of laws that connect geometry and information. This can change the emotional feeling of the universe. A purely empty universe can feel cold and indifferent, as though everything is scattered through a vast container. But a holographic universe suggests a cosmos where separation may not be the most basic fact. Beneath distance, there may be relationship. Beneath geometry, there may be information. Beneath the smooth appearance of space, there may be an order that does not look like the world we see, but gives that world its shape. This does not mean the universe has a purpose in the human sense. It does not prove that reality was designed, or that consciousness controls matter, or that every event carries a hidden message meant for us. Those are different claims, and the holographic principle does not require them. Its meaning is more restrained and more scientific. It suggests that information may play a fundamental role in how space and gravity are described. That is already profound enough without adding more than the evidence allows. One of the calmest implications is that reality may be less object-based than it appears. In everyday thinking, we imagine the universe as a collection of things: planets, stars, atoms, bodies, rooms, galaxies. But physics often describes nature through states, fields, symmetries, relationships, and transformations. A thing is not only a thing, it is a stable pattern in a wider system. A person is not just a shape occupying space. A person is matter, energy, chemistry, memory, perception, and time organized into a living process. From this perspective, holography does not reduce life to cold data. It invites us to see information as physical, not artificial. Information is not only something stored in computers or written in books. In physics, information means the distinctions that make one physical state different from another. The arrangement of molecules in a cell, the pattern of light reaching the eye, the structure of a memory in the brain, and the state of a field in space all involve physical information. If reality is holographic, then information is not separate from the world. It is one of the ways the world has structure. This gives a gentler meaning to being alive. You are not outside the universe looking in. You are a temporary, organized part of it. Your thoughts are not detached from physics. They arise from a living brain made of matter, shaped by evolution, chemistry, and experience. Your body is not separate from the cosmos. Its atoms came from older stars and cosmic processes. If space itself is also tied to information, then your existence is part of a universe that is not merely filled with structure, but perhaps built through structure at the deepest level. At the same time, the holographic idea should make us humble. It reminds us that human intuition is powerful but limited. The brain is excellent at navigating ordinary reality, avoiding danger, recognizing faces, finding food, understanding motion, building tools, remembering places. But it did not evolve to understand black hole entropy, quantum gravity, or the emergence of space-time. When physics tells us that reality may be unlike our direct impressions, it is not insulting common sense. It is simply extending beyond the range where common sense was designed to work. This has happened many times before. The universe has repeatedly turned out to be larger, older, stranger, and more subtle than human cultures first imagined. Earth was not the center. The Milky Way was not the whole cosmos. Matter was not solid in the simple way it felt. Time was not universal in the way it seemed. Each discovery took something away from our first impression, but gave back a larger reality. Holography may be another step in that pattern, not a loss of the world, but a widening of what the world could be. It also changes how we think about knowledge. To know reality may not mean finding one final picture that looks exactly like experience. It may mean finding descriptions that preserve relationships, predictions, and laws. A boundary description and an interior description may feel different, yet both may be valid if they capture the same physics. This is a quiet lesson in intellectual flexibility. Nature may not be obligated to use the categories most comfortable to human imagination. For us, this can be freeing. We do not need reality to be simple in order for life to matter. We do not need space to be fundamental for a walk through a quiet street to be real. We do not need matter to be solid in the old intuitive sense for touch to be meaningful. The world can be emergent and still be trustworthy. It can be encoded and still be present. It can be strange and still be home. If the universe is holographic, then perhaps the deepest lesson is that reality is not exhausted by appearance. The room may look still, yet fields are active within it. The night sky may look empty, yet it is crossed by light from ancient stars. A black hole may look like silence, yet it may contain clues about information and gravity. A boundary may look like an edge, yet it may hold the description of a depth. Again and again, science finds that the surface of things is only the beginning. There is also beauty in the patience of this mystery. The holographic principle is not complete as a description of our own universe. It remains part of an unfinished search for quantum gravity, a search that may take generations. But unfinished ideas can still be meaningful when they clarify the shape of the unknown. They show where our theories strain, where old assumptions weaken, and where new connections may be waiting. This is why the idea can be both scientific and calming. It asks us to live with uncertainty without turning uncertainty into fear. The unknown is not always a threat. Sometimes it is simply the space where understanding has not yet arrived. A mystery can be open, careful, and honest. It can invite attention without demanding anxiety. In that sense, The holographic universe is not only a question about physics, it is also a reminder that not everything vast must be solved in order to be peacefully held. So what does it mean for us? It means we live in a universe whose foundations may be more elegant than direct sight reveals. It means that space, time, gravity, matter, and information may be connected in ways that are only beginning to be understood. It means that being small in the cosmos does not mean being disconnected from it. The same laws that bend light near black holes also allow atoms to form, stars to shine, and nervous systems to become aware of the universe around them. And perhaps that is enough for the final thought. If reality is holographic, you are not less real. You are part of the projection and part of the physics that makes the projection meaningful. You are a brief pattern inside a vast order, not separate from the mystery, but included within it. Now the question can rest. The universe does not need to be solved tonight. Its depth can remain deeper than language, its boundaries quiet, its information hidden in the dark. The day can loosen, the body can grow heavy, and the mind can drift gently inside a reality that may be stranger than it seems, but still steady enough to hold you. My friend, if you're still awake, thank you for spending this quiet journey with me. Tonight, we followed one of the strangest ideas in modern physics, that reality may be holographic, not because it is false, but because space, gravity, and information may be connected in ways deeper than ordinary experience can show. And if your mind still wants to wander a little further, you can continue with another video and let the next mystery carry you gently into sleep. But if this is where the night ends for you, then let the question rest. You don't need to solve the universe tonight. Let the room become quiet, let the day fade away, and as always, my friend, sweet dreams among the stars.